So let's talk about improper integrals, okay? And sort of a weird name, right? Improper. Uh, Seems like it's something inappropriate. But what improper integrals basically are integrals over either infinite intervals or integrands that are unbounded, okay? Functions that have asymptotes that go up to infinity or minus infinity, or integrations over an infinite interval, okay? And these do come up in physical applications if you need to integrate, say you want to know the amount of decay for something over a very long time. Well, you'll take the limit as the time goes to infinity. The basic way to do these improper integrals over infinite intervals. Okay, so let's focus on that, and then we'll talk about unbounded integrands. But over infinite integrals, so if we want to intervals, so if we want to integrate from a to infinity, okay, so basically finding the area under the curve to the right of a, if you want to think about it that way, you write it in this form. Now, what does this mean? What does that mean when you put an infinity there? Here's what it means. Okay, now pay attention to that. This is the crux of the matter there. Okay, here's what that means. Is that you'll integrate from a to some arbitrary b and then take the limit as b goes to infinity. If you want to integrate from negative infinity to b, so everything you want the area under the curve to the left of b, then you'll integrate a to b and you'll take the limit as a goes to minus infinity. Okay, and if you're integrating for if you want to find the area under the curve from all the area under the curve over the whole entire real line, well, you do then you break up this integral up to some arbitrary point c. Now, it doesn't matter what c you choose; any real number will work. And then you integrate from a to that real number that you chose, and from c from the real number that you chose to b, and then you'll take two separate limits. Okay, they are two separate limits. Don't combine them. They're two separate limits, and you'll have then the limit as a goes to minus infinity for that, and you'll add then the limit as b goes to infinity for that integral. Okay. If these limits exist, we say that the improper integral converges. If the limit does not exist, we say diverges. So let's take a look at some concrete examples of doing this. So here we have e to the minus x, okay, and we want to integrate e to the minus x from 0 to infinity. And so again, we just use this basic form here, the limit as b goes to infinity from 0 to b. And so you integrate, and you'll have that arbitrary b there. You just leave it as b. Evaluate the integral just as you would any number. You just plug in b, okay? And then you take the limit as b goes to infinity for that. Now, e to the minus b as b goes to infinity is 0. Okay, the limit of that as b goes to infinity is 0. And so you'll get 1 minus 0, and that's just 1, okay? Now, what's that telling you? I mean, here's another way to look at that. If you take a look at e to the minus x, it looks like this. And it asymptotically approaches, okay? Now, you have an area under this, okay? There's an area. What this is telling you here is, for any value of x that you choose on the real line, it's going to be less than 1. But you keep approaching 1. So you keep adding area. But you'll never quite get to 1, but you keep approaching it. It's the same concept as limit. Okay? And that's somewhat, counterintuitive to get a grasp of, because there is an infinite amount of area there, right? It seems like there's an infinite amount of area. You could just keep adding more and more area. But what this is telling you is no matter how far you go along the x-axis, no matter how much area you keep trying to include, it's bounded by 1. And it approaches 1, okay? Let's take a look at another example, and this time over the entire real line, so minus infinity to infinity. And when we integrate this, we'll choose an arbitrary c, and I just sort of left it general there as c. And you could see that regardless of the c that you choose, that's going to cancel, right? So b, the limit here is for b and not c, and the limit here is for a and not c. And so you can see no matter what value of c that you chose, you have a plus arctan c here and a minus arctan c here. So it'll cancel. So it really does not matter what c you choose. You just choose a convenient c for you. And here the most convenient is c equals 0 because arctan of 0 is 0. And so those just fall out. Okay? And then you take the limit. Okay? You have two separate limits, a to minus infinity and b to infinity. And they're separate. And you'll get minus pi over 2 and pi over 2. So you'll get pi. And it's important here that you had different limits. Okay, you didn't just put the same a over there. You could really confuse yourself if you chose the variable a over here too. Okay, if you also had that ba and took the limit, because then you could factor out a limit and cancel, and you'll get 0. And that doesn't make much sense, right? Because these limits are different. One is going to infinity, the other is going to minus infinity. And so you do want to choose a different limit. And I mean, even if the limits were going to the same place, you don't want to be so restrictive that, to choose the same variable, because it means that, there you're not just saying they're going to the same place, but they're going to the same place at the same rate, and that's not necessary. Okay, so make sure that the limits are taken separately, and you use different values for the or different symbols for the point that you take the limit of. Let's also take a look at functions of the form 1 over xp. And now we'll look at it for all real numbers, but of course, only when p is positive do we sort of have something that could potentially give us a bounded or convergent improper integral. So we're going to look at integrating this from 1 to infinity. Okay, if p does not equal 1, because of course the integral of 1 over x is natural log of x, so if p does not equal 1, then you get this general form. Okay, now this is the general form as long as p is not equal to 1. And now pay attention to this part. Okay, we're going to take the limit as b goes to infinity. So if 1 minus p is positive, well, we're going to get a divergent result. Okay? But if 1 minus p is negative, then we'll get convergence. And so we'll break it up. We'll break up this problem into different cases. And here we have the first case where p is strictly greater than 1. If p is strictly greater than 1, then p minus 1 is positive, which means 1 minus p is negative. And so you could write this, b to the 1 minus p is 1 over b to the p minus 1, right? If you take the inverse, you multiply by negative 1. And you could see then that p minus 1 in that case is positive, and as b goes to infinity, you get 0, okay? And you get this final result for that improper integral. For the case of p is strictly less than 1, well, then we have 1 minus p is greater than 1, and then b to the 1 minus p is divergent, right? So you'll get plus infinity there when as b goes to infinity. Okay, so it's a divergent integral. What about when p equals 1? I mean, that was the special case because we can't write it in this form. Well, you integrate this and you'll get a natural log of x. Then take the limit and put the bounds and take the limit. Natural log of 1 is 0, and that's why that's not showing up there. But when you take the limit of natural log of b, you get infinity. And so this is a sort of interesting result, right? What's this telling us? It's telling us that if we have, for example, if this is 1 over x squared, we don't want to draw it that way. We'll have 1 over x squared here. Say this is 1 over x squared. And say this is 1 over x, okay? You know, they'll actually meet at the value of 1, okay? But it still falls off. Okay, this is 1 over x. Okay, so this here will be 1 over x. And we're getting an interesting result, okay? So for 1 over x squared, that's p equals 2. So with p equals 2, you'll have 1 over 2 minus 1, or 1/2. And what that's telling you is that, you know, even though this is an infinite interval, even if you keep adding more and more, you know, sub-intervals, you'll never quite get to 1/2. Okay, no matter how far you go by adding more and more areas, you'll never quite get to 1/2. It's the limit. But 1 over x actually approaches the x-axis, right? The limit of 1 over x as x goes to infinity is 0, just like 1 over x squared. But this integral, this improper integral, is divergent. And what does that mean? That means if you choose any number, say 50, what that's telling you here is that the area under 1 over x, if we go far enough, we'll get an area of 50. Okay? If we go far enough and keep adding areas, we'll get to the number 50. What about 100? Again, we just keep going farther to the right there, on the positive x-axis. And what about 100? What about 1 million? What about 10 trillion? No matter what number you throw out, no matter how large it is, you could keep adding more and more areas. Now, it might take a very long time, right? You got to get very far along the positive x-axis. But if you keep adding more and more area, you will eventually get to that number. With 1 over x squared, that's telling you can't do that. After 1/2, you can't possibly get an area greater than 1/2, no matter how far you go to the right. Okay? And so that's what's telling you. That's what that's telling you. Okay? So anything, any value p strictly greater than 1 will give you a bounded or convergent improper integral for that integral from 1 to infinity. And any value less than 1 or equal to 1 will be divergent. Okay? So that's an interesting result there. Well, what about when we have unbounded integrands? Okay, something like this. Okay, you can see you have asymptotes there, and the function is unbounded. It just it goes up to infinity. So how do we deal with problems like that, where in our interval of integration we have this asymptotic behavior, then the function is unbounded there. So consider that interval there with parentheses there, not a square bracket. So it means we don't include a, okay, because a is not even defined. The function's not even defined at a. And suppose that the limit, as you approach a from the right, okay, so we're integrating over a to b here. So, our problem is at a, the function is not defined at a, it's unbounded. It either goes to plus or minus infinity. Well, then how do we what does this mean? What does that mean when you're integrating from a to b and the function's unbounded at a? It means that you approach a from the right, okay, if you're integrating over this. Well, what about an interval a to b when the function is unbounded at b, so the right at the right end of your interval, okay? In this case, you approach b from the left, okay, and you have, you know, it's divergent at b, and so you'll take the limit and approach b from the left, okay? So that's what this technically means. So you integrate from a to c, where c is arbitrary, and then you'll take the limit as c goes to b from the left, okay? And what if you're integrating from a to b and the offending point is p, somewhere, you know, in between a and b? So not necessarily a to b, and f is unbounded at p. So what do you do? Well, in this case, you'll break up your integral from a to p, and then from p to b, and then you'll approach p from the left when you're integrating from a, and then you'll approach it from the right when you're integrating to b, okay? So if you're integrating from a, you approach it from the left, and you want to complete the integration, and so you'll approach p from the right over here, okay? And so let's take a look at a concrete example. Here we have that this integral over here, we have a asymptote at 2. And so if you approach 2 from the right, you get a limit of plus infinity. If you approach it from the left, you get a limit of minus infinity there. And so how do you integrate that? You want to integrate from 1 to 10, and 2 is the offending term, right? That's where the function's unbounded. So you'll break up your integral into two different integrals. One where you start at 1 and then integrate to c, where c is approaching 2 from the left, okay? And then another integral from where you integrate to 10, okay, the right end of your interval, and you approach 2 from the right, okay? So that's what's going on there, and we'll just leave that d arbitrary. So we integrate and we plug in c and d in our bounds, okay? And we take the limit here as c approaches 2 from the left, and we take the limit here as d approaches 2 from the right, and we end up getting 9/2. So despite this function being unbounded, the area does have a limit, okay, and that's 9/2. So if you keep, you know, getting closer and closer to 2 and adding more and more areas, okay, from the left and right, then you have a bound of 9/2, okay? So you can't ever get more area than 9/2, okay? And you know, over here you're actually subtracting area rather than adding it. You're subtracting area. No matter how much you subtract, no matter how much you add, you know, you're going to get to a limit of 9/2. That's what that's telling you over there. So okay, and we could do one more example. Here it's -3 to 3. And here the offending terms are the right and left endpoints, okay? Both of them have unbounded behavior there. So if you put a -3 there, you're going to get a 0 on the bottom. Or if you put a 3, you're going to get a 0 on the bottom. Okay, but this is a symmetric function about the y-axis, and so you could multiply by 2 and take the integral from 0 to 3. And, well, you know, this is at the right endpoint. 0 is not a problem, but at the right we do have unbounded behavior. And so we're going to integrate from 0 to c and then take the limit as c goes to 3 from the left, okay? And plugging that in and taking the limit, we get pi over there. Finally, we could discuss this theorem here, the comparison test for improper integrals. Suppose the functions f and g are continuous on the interval a to infinity. And the f is greater than g, greater than or equal to g, and both of them are positive, okay? In that case, right? So g is positive. Then for x is greater than a, right, the left point of the interval, we have that if f converges, then g converges. That makes sense, right? If f converges, then g converges because f is greater than g, okay? So if f is greater than g and it converges, then g must converge. Of course, given that it's greater than 0, right? You could, if we didn't have that constraint, then you could have sort of a negative infinity problem there. But if we have that constraint there, then this makes sense. On the other hand, if g diverges, so if f is greater than g, but g is diverging, right, the improper integral is diverging over this infinite interval, then f must diverge because f is greater than g, okay? So if something is smaller but infinite, right, then the greater value should also be infinite. That's kind of what that's saying, okay? And so we could use the comparison test to look at this integral here. You get e to the minus x squared. But from 1 to infinity, e to the minus x is actually greater than e to the minus x squared. So without actually evaluating the integral, I mean, we did e to the minus x up here, and we found that, it was 1. And so, if that's greater and convergent, well, this is also going to be convergent. So we could at least say that it's convergent. Now, it doesn't mean it's going to converge to the same value, right? It doesn't mean that it'll be 1. But sometimes all you want is the fact that the integral converges. Okay, and so this converges because e to the minus x is greater than e to the minus x squared, and we know that e to the minus x from 1 to infinity, the integral will converge. Okay, and here's just a quick note about something called Cauchy principal value that you might run into. We don't really consider that here, but what you're doing with Cauchy principal values, I mean, I told you to take limits where you separate the two limits from the left endpoint and the right endpoint. There is something called a Cauchy principal value where you actually take one limit and you do it symmetrically from minus r to r. Okay, and so you'll take those limits symmetrically. That's a different matter altogether. Or you approach the, and this is for infinite intervals. For unbounded integrands, you'll approach the offending point where there's where the function is unbounded symmetrically, with this epsilon. So you'll take the limit as epsilon goes to 0, and you'll have a c minus epsilon and c plus epsilon. So here, c is where there's an offending term. Okay. But that's something altogether different, and it's restrictive, and you have to do things symmetrically there. And so you can't always assume that if something works with the principal value that it will work with our method, okay, which is more general. And so that's something to keep in mind there in case you are into it in the literature.